Welcome back to the Deep Dive, where we take the vast, complex world of technical documentation and really try to distill it down to the pure, high-impact insights you need.
Yeah, and today we're undertaking a pretty critical deep dive for, well, anyone building an iOS application. We're essentially mapping out the entire landscape of data persistence and storage,
Right, everything from, like, a single flag that remembers dark mode.
all the way up to complex relational data sets and even, real-time synchronization. It covers a lot of ground.
Exactly. And if you're a developer, you know this is probably the single most important architectural decision, maybe besides your UI framework, is how you actually handle data.
Uh-huh. Are you prioritizing security? Or is speed the main thing? What about structure?
Yeah, the sources we're looking at today give us this comprehensive roadmap for choosing the right tool. Whether it's UserDefaults, Keychain, Core Data, Skelite, or maybe Realm.
Each one fits a specific data task, doesn't it?
It does.
So our goal here, really, is to equip you with the deep comparison points you need so you can confidently differentiate these systems.
And crucially, avoid those common, sometimes costly mistakes.
Oh, absolutely. Like misusing a simple preference store for, say, sensitive credentials. That's a classic error.
Okay, let's unpack this.
All right, so first up, user defaults. This one's, well, it's everywhere. It's probably the most ubiquitous, but maybe also the most frequently misused storage solution in iOS development.
Okay.
At its core, it's just a lightweight key-value system. Simple as that. Its defining characteristic, speed for small bits of data, and it sticks around, it persists across app launches.
So it's really the perfect place for configuration settings, isn't it? When we look at the ideal use cases, they're almost purely focused on user interaction and like state flags.
Exactly. Things like user preferences is dark mode on. What font size did the user pick?
Simple app settings too,
Yeah,
right? Like
right.
notifications enabled or disabled.
Yeah, or even lightweight state tracking, like checking if the user finished the onboarding tutorial that first time they opened the app.
Gotcha. And how does it actually store this stuff?
Well, the mechanism kind of dictates its limitations. All that data gets serialized into a property list file, a PLIS file.
Okay.
And that file just sits inside the app's sandbox container. The neat thing is, it's loaded into memory really quickly when the app launches.
So that gives you fast access. Makes sense for settings you need instantly available.
Precisely. But we really need to hammer on the not recommended list here. This is super important if we're building solid knowledge. We've got to stress why this is not a general-purpose storage solution.
Okay, lay it out for us. What should we absolutely not do?
Rule number 1, never use it for large data. Absolutely no images, no big files, and definitely not huge JSON objects or like complex arrays with hundreds and hundreds of items.
Right, it's just not built for that scale.
Not at all. And rule number 2, even more critical, never, ever sensitive data.
Okay, this is the bright line.
This is the hard line. If it's a password, an API token, authentication credentials, anything that could compromise user security, it is strictly forbidden from user defaults, period.
So given those limits, what can it actually store directly without needing painful encoding steps?
Well, it's limited to those basic PLIST-compatible types. We're talking simple stuff: string, int, float, double, bool, URLs, and dates.
Okay, the primitives.
Yeah, the primitives. You can store arrays and dictionaries too, but only if everything inside them is also one of those supported types.
Okay. So what if I have my own custom Swift struct or class?
Right, that's where it gets tricky. If you try to store a custom object, you must first serialize it into raw data. Usually you'd use the codable protocol in modern Swift.
Or in Seeds Archiver for older stuff?
Exactly, for older legacy objects. But honestly, if you find yourself doing this serialization dance frequently for user defaults, you are almost certainly using the wrong persistence tool. It's a major red flag.
That makes sense. Okay, let's shift gears slightly. You mentioned advanced techniques. The first one sounds really important: sharing data outside the app's normal container. This comes up a lot with extensions, right?
It does. That's where the concept of custom suites comes in. See, normally when you just use userdefaults.standard, that data is completely locked within your app's specific sandbox. It can't get out.
Isolated.
Totally isolated. But say you develop an app that also has a widget or maybe an Apple Watch complication or even a share extension.
Those are like separate little mini apps, aren't they?
Exactly. They run in their own sandboxes. So if you want them to share preferences like the theme color or the user's display name, they need a common, secure place to look.
And that's where app groups come into the picture.
Correct. App groups are the fundamental mechanism Apple provides for this. They essentially grant a shared security container that sits outside the individual application sandboxes, but is accessible only to apps from the same developer team.
Okay, so you set that up in the developer portal.
Yep. You establish an app group identifier there, something like group.com.yourcompany.myapp. Then in your code, instead of .standard, you initialize user defaults using UserDefaults suite name .group.com.yourcompany.myapp.
And suddenly, the main app and the widget can both read and write to the same shared preference store.
Precisely. Your widget can pull the theme color set by the main app, maintaining that crucial consistency across your whole app ecosystem. It's super useful.
Okay, that's a great practical tip. What about the second technique? You mentioned type-safe user defaults using property wrappers. This sounds like a code quality improvement.
Oh, it's a massive improvement. We've all seen that nightmare code, haven't we, where user defaults keys are just hard-coded strings scattered everywhere.
Yes. Leads to typos or worse.
Or worse, accidental type mismatches. You try to read a key you thought was a Boolean, but you accidentally save it as a string, and boom, runtime crash.
You've been there.
Property wrappers solve this beautifully. You essentially create a custom wrapper around the user defaults access. This wrapper handles the key management internally and, crucially, enforces type checking at compile time.
So the compiler catches the errors, not the user at runtime.
Exactly. If you define a property wrapper for, say, is dark mode enabled and declare it as expecting a bool, the compiler guarantees that any code reading or writing through that wrapper must treat it as a Boolean.
Nice. So it prevents those classic runtime headaches and just makes your whole configuration layer dramatically cleaner and safer.
Totally. No more magic strings, much less chance of errors. Highly recommended.
Okay, now, here's where it gets really interesting, you said, the performance warnings. This feels like where a lot of production apps might stumble if they misuse this seemingly simple tool.
This is absolutely where things go wrong.
So let's say I ignore the advice. I decide to shove, 10 megabytes of JSON into a single user defaults key. What are the immediate painful consequences?
Oh, it's bad. The core problem lies in how user defaults loads and saves data. Remember that list file?
Yeah.
Every single read-or-write operation, even if you're just changing one tiny Boolean flag, forces iOS to serialize or deserialize the entire list file, not just the value you change, the whole thing.
Wow, okay. So if that file is 10 megs,
then every time you save anything, iOS has to write out that entire 10 MB file. And every time you read anything, it has to parse the entire 10 MB file. You hit immediate critical performance degradation.
And I guess the most noticeable symptom for the user would be app launch delay.
Absolutely the most noticeable. User defaults is one of the very first things loaded into memory when your app starts up. So if you've got a massive list file, the operating system has to spend precious milliseconds, maybe even seconds, just deserializing that huge blob of data before your UI can even appear. It makes your app feel sluggish right from the start.
That's terrible user experience.
It is. And it doesn't stop there. Because those objects are loaded into RAM and they stay there for the lifetime of the app, you're generating unnecessary memory overhead. That 10 MB JSON blob is just sitting in memory, potentially crowding out other important things.
Yikes. Any other risks?
Yes, data corruption risk actually increases. Writing large amounts of data is inherently more prone to interruption. If your app gets terminated by the system mid-write while saving that giant list, the entire preference file could become corrupted and unreadable on the next launch.
Ouch. Losing all settings.
Potentially, yes. And one last thing to emphasize. User defaults is not inherently thread-safe for heavy concurrent writes. If you have multiple background threads trying to update different preferences simultaneously without proper synchronization, you can easily run into race conditions and unpredictable behavior.
Okay, message received loud and clear. User defaults is for small, non-sensitive configuration data only. Misuse it at your peril, especially regarding performance.
Precisely. Use it for what it's good at and stay away from the danger zones.
So we've drawn a very clear line. Lightweight, non-sensitive stuff, user defaults, but anything that is sensitive absolutely requires the keychain.
That's the rule. The keychain is iOS's dedicated, secure, hardware-backed storage system. Its purpose is really singular, to be the secure vault for sensitive information.
Okay, so what falls into that sensitive category?
Think user passwords, obviously.
Oh,
Builder-truth tokens for third-party services, API keys for your backend, Certificates, basically anything required for user authentication or establishing secure connections to external systems. If it getting leaked would be bad news, it belongs in the keychain.
Got it. Now, structurally, it's also a key value store, isn't it? Similar to user defaults in that basic way.
It is, fundamentally. You store data associated with a key, but the core difference isn't the storage pattern. It boils down entirely to the security architecture.
Right, so why is the keychain fundamentally more secure than that user defaults plist file?
Because user defaults data, as we said, is stored unencrypted in a plain file on the device. Anyone who can access that file can potentially read it. The keychain, on the other hand, is encrypted automatically by the operating system.
And it's strong encryption, right?
Very strong. It often leverages hardware encryption features tied directly to the secure enclave processor on modern iPhones. And access is further protected by the user's device passcode or their Touch ID or Face ID biometrics.
So it makes it virtually impossible for malicious actors or even other apps on the same device to just sniff out those credentials.
Exactly. It's a hardened system-level secure storage facility.
Okay, that's the security difference. You also mentioned another major distinction, persistence. How does that differ?
Right. This is also crucial. When a user deletes your app from their phone, what happens to the user defaults data?
It's gone, right? Since it lives in the app sandbox, deleting the app deletes the sandbox.
Correct. Wiped out immediately. But keychain data behaves differently. If you configure the keychain item with the right access controls, the data can actually persist even if the app is deleted and later reinstalled.
Oh, wow. That's a huge user experience benefit, isn't it?
Massive. Imagine the user deletes your app, maybe to free up space, then reinstalls it a month later. If you stored their login token in the keychain correctly, the reinstalled app can retrieve that token, and the user might be automatically logged back in, skipping the whole tedious reauthentication process.
Well, that's slick. Users would definitely appreciate that.
They really do. It removes a significant point of friction.
Okay, let's circle back to sharing data between apps.
Right.
We talked about app groups for sharing user defaults. How does the keychain handle sharing sensitive data across, say, a developer's suite of related applications?
It uses a very similar concept, but it's called keychain access groups.
Okay, makes sense.
Similar principle to app groups. You define an access group identifier, again, usually in the developer portal. This identifier allows multiple apps or extensions that are signed by the same registered developer team to securely read and write specific items stored in the keychain under that group.
So this is perfect for enabling that single sign-on experience you mentioned earlier.
Exactly. It's paramount for that. If your main app performs the initial login and stores the authentication token in a shared keychain access group, your companion utility app or your widget can then securely retrieve that same token without ever needing to ask the user for their password again.
Seamless integration across the ecosystem.
That's the goal. Secure and seamless.
Okay, the analysis here seems crystal clear for you, the developer listening. Never, ever prioritize convenience over security. The slight extra complexity involved in using the Keychain API compared to user defaults. Well, it's just a non-negotiable step when you're handling anything like authentication data or secrets.
Absolutely non-negotiable. The potential fallout from leaking sensitive data is just too high. Use the right tool for the job, and for sensitive data, that tool is always the keychain.
All right, we've handled the quick wins preferences with user defaults, security with Keychain, but let's be honest, most modern apps deal with more complex stuff, right? Entities like users, posts, maybe financial transactions, and importantly, the relationships between them.
Exactly. This moves us squarely into the realm of structured data persistence. And the two heavyweights in the Apple ecosystem here have traditionally been core data and SQLite.
Okay, so this is a big architectural shift we're talking about now.
It really is. We're moving away from simple key value lookups, give me the value for key X. Now we're talking about systems that need to handle complex querying, indexing for performance, and managing potentially intricate object relationships, #TechHatchAppleA, defining the database landscape. So before we even start comparing them feature by feature, we absolutely have to clear up some common terminology confusion, especially around core data.
Okay, let's define our terms. What is SQLite?
SQLite is pretty straightforward. It is a lightweight, file-based relational database engine. Think traditional database tables, columns, rows, primary keys, foreign keys. You interact with it by writing raw SQL query strings.
And it's built into iOS.
Yes, iOS includes the SQL library by default, so you have direct, low-level access to this powerful relational database engine right out of the box.
Okay, simple enough. Now, core data. This is where the confusion often comes in, right? People call it a database, but that's not quite accurate.
That's the key misconception. Our sources are really clear on this. Core data is not technically a database itself. It's Apple's framework designed for managing the model layer of your application. It deals with the object graph.
Object graph. What does that mean in practice?
It means that as a developer, you interact primarily with your data using native Swift or Objective-C objects, things you define as entities, with attributes and relationships rather than messing around with raw SQL strings and database rows.
So it's like an abstraction layer on top of the actual storage.
Exactly. It's best understood as an object relational mapper, or ORM. It maps between your application's objects and how they're actually stored. And here's the important part. Core data can, and very often does, use SwiftUI as its underlying persistent store, but it could also use an in-memory store or a binary format. Core data itself is the management layer, not the storage engine. ##B, feature by feature comparison. Okay, so now that we've defined them, if we connect this back to the bigger picture for the developer listening, the fundamental choice between core data and SwiftUI often rests on this. Do you prefer the abstraction, the high-level features, and the integrated object management that core data offers? Versus the raw speed, the potential for cross-platform portability, and the fine-grained, granular control over your data that writing direct SQL with SwiftUI provides.
Okay, let's break down some key differences then. Starting with the data model itself. How do you define your data structure in each?
Right. With core data, you typically define your entities, their attributes like string, int, date, and the relationships between them visually using a dedicated data model editor right inside Xcode. It's a graphical process.
And the SwiftUI?
SwiftUI is traditional database stuff. You define your structure using SQL's create table commands. You specify table names, column names, data types like text, integer, real, and define primary and foreign keys manually using SQL syntax.
That difference leads right into relationships, which you mentioned. This seems like a massive distinction in practice.
It's huge. Core data is designed around object relationships. You can visually define one-to-one, one-to-many, and many-to-many relationships between your entities in the Xcode editor.
And core data handles the tricky parts.
Yes, core data automatically manages the underlying foreign key constraints in the database if you're using SQL underneath, and, more importantly, makes traversing those relationships in your code incredibly easy. You can just access related objects directly, like author.posts or post.author.
How does that compare to SwiftUI?
With SwiftUI, you're doing it all manually. You have to explicitly define the foreign key columns in your create table statements. And when you want to retrieve related data, you have to write the SQL join clauses yourself, which can get complex pretty quickly, especially for many-to-many relationships.
Okay, that's a significant difference in developer effort right there. What about other built-in features, things that save you from writing boilerplate code? This feels like core data's home turf.
It absolutely is. Core data comes packed with features that are vital for building complex, stable applications. For instance, it offers automatic change tracking.
What does that mean exactly?
It means core data automatically keeps track of every object that's been fetched, modified, inserted, or deleted within a given work session, what it calls a managed object context. This makes it trivial to know exactly what needs to be saved back to the database.
Okay, that's handy. What else?
It provides built-in undo and read capabilities with very little effort on your part. Imagine letting users undo complex data changes. Core data handles much of the state management for that. It even attempts lightweight automatic migration.
Migrations. You mean like when I change my data schema?
Yeah.
Add a new field or something?
Exactly. If you only make simple changes to your data model, like adding a new attribute, core data can often automatically migrate the existing database file to the new schema version without you writing any migration gun. For more complex changes, you need manual migration, but the lightweight stuff is often handled.
Wow, okay. And SwiftUI's position on all this? Change tracking, undo, migrations.
Fundamentally, those features are absent in raw SwiftUI. If you want under-redo functionality with SwiftUI, you have to architect and build that entire system yourself.
Track previous states, manage the undo stack.
All of it. If you want database migrations when your schema changes, and your schema will change, you have to write the alter table SQL commands yourself, manage schema version numbers, and handle the whole update process manually.
So that's the boilerplate tax you mentioned. You pay for the simplicity and control of SwiftUI by having to build these common framework features yourself.
Precisely. That's the core trade-off. Which brings us to complexity versus transparency. Core data undeniably has a much higher initial learning curve.
Yeah, you hear that a lot.
Mastering its concepts, the Managed Object Contest, MOC, the persistent store coordinator, the threading rules, it's genuinely tough. But once you climb that curve, it offers phenomenal power and features that accelerate development significantly.
And Squice.
SQUITE is conceptually simpler to grasp. Tables, columns, SQL queries. Most developers have some familiarity with that, but because it lacks that high-level abstraction, you end up writing far more manual code to achieve the same results you might get easily with core data. It's more transparent, you see exactly what SQL is running, but less abstract.
Okay, one last major differentiator. Cross-platform needs. This seems pretty black and white.
It mostly is. Core Data is an Apple-specific framework. It works beautifully on iOS, macOS, watchOS, tvOS, but that's it.
So if my project requires the same database code or the same schema definitions to work seamlessly on, say, an Android app or a Windows desktop app, or maybe a shared library used by a web backend,
Then Core Data is simply not an option for that shared component. SwiLite, being a C library, is incredibly portable. It runs virtually everywhere. So if your architecture demands that your data layer must transcend the Apple ecosystem, SwiLite becomes a very powerful, often necessary choice.
right? Because you can share that SwiLite database file and the code that interacts with it across different platforms.
Exactly. That's a major architectural driver for choosing SwiLite in many larger projects.
Okay, so if a developer decides core data is the right fit, maybe for an Apple-only app that needs those rich features, they absolutely must understand its internal architecture to use it effectively,
Yeah.
right? Especially avoiding those pitfalls like threading issues.
Absolutely critical. Fortunately, since iOS 10, Apple introduced the NS persistent container, which significantly simplifies setting up and managing the whole core data stack.
Okay, so what's in that stack? What are the key pieces managed by this container?
The stack essentially consists of three core, tightly integrated components working together. First, you have the NS managed object model.
That's the visual thing in Xcode.
Exactly. That's the blueprint. It's the object representation of that .xc data model file you edit. It defines your schema. The entities, like user, post, their attributes, name, timestamp, and the relationships post's author between them.
Okay, blueprint, got it. What's next?
Second is the NS persistent store coordinator. This is a really crucial piece, often misunderstood. Think of it as the conductor or the traffic cop of the stack.
Okay, how so?
Its job is to mediate between the object model, the blueprint, and the actual persistent store on disk. It knows how to talk to different store types, SQL8, binary, in-memory. It's the critical abstraction layer.
Ah, so it connects the object world to the storage world.
Precisely. It shields the rest of your application, particularly the part that deals with objects, from having to know how the data is actually being stored underneath. It just presents a consistent interface.
Clever. Okay, model coordinator. What's the third piece?
The third piece is arguably the one you interact with the most directly. The NS managed object context, usually just called the MOC.
Right, the MOC. This sounds important.
It's the engine room, or maybe better, the memory scratch pad. When you fetch data from the store, Core Data creates corresponding NS-managed object instances that live inside a MOC. When you modify these objects or create new ones, those changes initially only exist within this MOC scratchpad.
So changes aren't written to disk immediately.
Not at all. The MOC tracks all insertions, deletions, and updates you make to the objects it manages. Nothing gets permanently written to the persistent store file via the coordinator until you explicitly call the save method on the context.
Okay, that makes sense for grouping changes. But the existence of this MOC scratchpad immediately brings us to what you call the most complex and critical rule in core data development: concurrency and threading.
Yes. This cannot be emphasized enough. The NS-managed object context is fundamentally not thread safe.
Not thread safe. What does that mean in practice, and why is it so dangerous?
It means you must adhere strictly to this rule. A specific MOC instance must only ever be accessed on the dispatch queue, the thread, on which it was originally created or assigned.
And if you violate that rule, let's say I fetch an object on a background queue's MOC and then try to update one of its properties directly on the main UI thread using that same object reference.
You're asking for trouble. Best case scenario, an immediate runtime crash, which is annoying but at least tells you something's wrong. Worst case, silent data corruption. The internal state of the MOC becomes inconsistent, leading to unpredictable behavior, potentially saving garbage data, and creating bugs that are incredibly difficult to track down later.
Yikes. Okay, so how do developers practically manage this? How do you work with core data across different threads safely?
The NS persistent container helps a lot here by providing pre-configured contexts designed for specific purposes. Firstly, it gives you the view context.
Okay, view context. It sounds like it's for the UI.
Exactly. The view context is automatically associated with the main dispatch queue. This is the context you should use for any data needed to update your UI, or for short, simple changes triggered directly by user interaction on the main thread.
Got it. But what about long-running tasks? Like importing a massive JSON file from a network request. I definitely don't want to do that on the main thread.
Absolutely not. For heavy asynchronous operations like that, you use the container's new background context method. This creates a separate independent MOC that operates on its own private background queue.
Okay, separate context, separate queue.
Yeah.
But how do I ensure my code actually runs on that background context's queue?
You have to use the context's dedicated methods for queue management. Perform for asynchronous execution, or perform and for synchronous execution. You wrap the block of code that needs to interact with the background MOC inside one of these calls.
Like this, background context.perform. Safe to access background MOC here.
Precisely. That ensures your core data operations happen on the correct queue, preventing those dangerous cross-thread access violations.
Now, there's also this idea of parent and child contexts, right? And how changes flow between them.
Yes, that's a common pattern for managing discrete units of work, especially if you want operations to be cancelable. You can create a background MOC as a child of the main view context. You do your work and inserts updates in the child context.
Okay.
If you save the child context, its changes are not written to the persistent store yet. Instead, they are pushed up and registered within its parent context, the view context in this case.
Ah, so the changes are now staged in the parent.
Exactly. Only when you subsequently save the parent view context do those changes finally get passed down through the coordinator and written permanently to the disk file. This hierarchical saving is vital for creating atomic operations. You can do a bunch of work in a child, and if something goes wrong, you just discard the child context without saving it, and the parent context and the persistent store remain untouched.
That's a really powerful pattern for data integrity. Okay, shifting from safety to performance. You mentioned fetching, say, 10,000 user records. Loading all of their data attributes into RAM instantly sounds like a terrible idea.
It's a recipe for memory exhaustion and crashes, absolutely. This is where one of Core Data's most brilliant optimization features comes in, faulting.
Faulting. Okay, break that down for us.
Faulting is essentially Core Data's built-in lazy loading mechanism. When you execute a fetch request, Core Data doesn't necessarily load all the attribute data for all the objects that match your request right away.
So what does it load?
Instead, it often creates placeholder objects, which are called faults. These fault objects are lightweight. They contain the bare minimum information needed to identify the real object, like its unique ID, but haven't yet pulled the actual attribute values, like name, email, age, from the database file.
Okay, so I get back an array of these placeholder objects.
You get an array that looks like it contains fully realized objects, but under the hood, many of them might be faults. The magic happens when your code actually tries to access a specific property on one of those objects for the first time.
Like if I try to read user.name.
Exactly. At that precise moment, Core Data detects it's a fault, goes back to the persistent store coordinator, fetches just the required data for that specific object, populates its attributes, and fires the fault, turning it into a normal, fully realized, managed object.
Wow. So it only loads the data precisely when needed. That's incredibly efficient for memory.
It's lazy loading at its finest, and it's fundamental to how Core Data can handle potentially massive data sets without immediately blowing up your app's memory footprint.
So if I have, say, a user entity with a profile image data attribute that could be large, and I fetch 10,000 users, but only display their names in a list.
Core Data will likely only fetch the name data, or maybe just the object IDs initially. It won't touch those potentially large profile image data blobs until your code specifically tries to access user.profile image data for a particular user, maybe when the user taps on their profile.
That's fantastic. Are there ways developers can help Core Data optimize fetching even further?
Absolutely. While faulting is automatic, you can guide Core Data. Firstly, use properties to fetch on your NSFetch request. If you know you only need the name and email attributes for a list view, explicitly tell Core Data to only fetch those properties.
You don't fetch the whole object if you don't need it.
Exactly. It reduces the amount of data pulled from disk and the initial memory footprint even before faulting comes into play. Secondly, for potentially very large result sets, use fetch batch size.
Batch size. Does that chunk the results?
Precisely. Setting a fetch batch size, for example to 50 or 100, tells core data to fetch the object IDs in batches. It still returns a single array representing all matching objects, but it manages the underlying data fetching and faulting more efficiently in chunks, preventing the managed object context from being overwhelmed by trying to handle, say, 100,000 objects all at once.
Okay, properties to fetch and fetch batch size.
Yeah.
Good practical tips. Finally, let's talk about the UI integration. This is often hailed as Core Data's killer feature, especially for table and collection views. The NSFetch Results Controller, or FRC.
Ah, the FRC. Yes, it's incredibly powerful. Think of it as the ultimate glue between your core data persistent store and Apple's UI frameworks, specifically UItable view and UI collection view.
How does it work? What does it actually do?
It acts as a highly sophisticated middleware. You configure an FRC with a specific fetch request. You gfetch all tasks sorted by due date. The FRC then executes that fetch and, crucially, registers itself to listen for relevant changes occurring in the managed object context you associate it with.
So it watches the MOC for changes related to its fetch request.
Exactly. When data that matches its request is inserted, deleted, updated, or even just moved in terms of order, the MOC posts notifications. The FRC receives these low-level notifications and intelligently translates them into high-level, UI-friendly change descriptions.
Like what kind of descriptions?
It tells you precisely which objects were changed and at which index paths, section and row, they were before the change and where they are after the change. It gives you specific instructions like insert a row at index path 05, delete the row at index path 12, update the row at index path 01, or move the row from 03 to 00.
Wow. So instead of me having to refetch all the data and just call tableview.reload
Yeah.
which isn't animated.
The FRC gives you the exact fine-grained information you need to call the table view's batch update methods. Begin updates, insert rows, delete rows, move rows, end updates. This allows for smooth, automatic animations in your UI as the underlying data changes.
That must eliminate an immense amount of complex boilerplate code for tracking changes and calculating index path updates manually.
Immense. It's one of the primary reasons developers choose core data, especially for complex list-based UIs that need to react dynamically to data changes. The FRC handles that synchronization beautifully.
Okay, that's a deep dive into core data. Now let's pivot back to its counterpart, raw Squeet. If core data gives you that rich abstraction and feature set, Squeetle is all about direct control and often raw performance if used correctly.
Exactly. Now, when you decide to use SqueetLite directly in an iOS app, you have a few implementation options. At the very bottom layer, you can use the low-level C API that Apple includes with iOS, libsclite 3.
Using C in Swift, that sounds potentially painful.
It can be. Using the C API gives you the absolute maximum theoretical speed because there are 0 abstraction layers. But it's incredibly verbose. You're dealing with C pointers, manual memory management for strings, and C structs. It's very error-prone and doesn't integrate nicely at all with modern Swift features like codable or strong typing.
Okay, so probably not the first choice for most people unless they have extreme performance needs. What are the alternatives?
The most common approach for years was to use a third-party wrapper library. The classic one is FMDB, an Objective-C wrapper that makes the C API much more manageable.
FMDB, I've seen that around.
It provides an Objective-C object layer over the C functions, handles statement preparation, result set iteration, and makes things generally safer and easier. More recently, several excellent Swift-native SQLite libraries have emerged, like GRDB Swift or Squalite.Swift.
And what's the benefit of using a modern Swift wrapper like GRDB over something like FMDB or even the C API?
The primary trade-off is usually a tiny bit of performance overhead from the Swift abstraction layers versus a massive gain in safety, maintainability, and developer ergonomics. These Swift libraries offer compile-time SQL checking sometimes, type safety, seamless integration with Codable for mapping database rows directly to your Swift structs, better concurrency management, and just a much more pleasant Swifty ATI.
So for most projects starting today, a Swift wrapper seems like the way to go.
For the vast majority of projects, yes. The slight performance difference compared to raw C is almost always negligible compared to the huge increase in safety, reduced boilerplate, and faster development velocity you get from a good Swift wrapper.
Okay, so you've chosen your wrapper. Since you're writing the SQL yourself, or the wrapper helps you generate it, performance now heavily relies on good database practices, right? So particularly indexing.
Absolutely critical. Indexing is paramount in SQLite, just like in any relational database. If you don't have the right indexes, query performance will degrade dramatically, often logarithmically, as your database grows larger.
So what's the rule of thumb? Which columns should you index?
The simple rule is Any column that you frequently use in a where clause for filtering, a join clause for linking tables, or an order by clause for sorting should almost certainly have an index created on it.
And without an index on, say, a column in my where clause?
Without an index, SQLite is forced to perform a full table scan. It has to literally read through every single row in the table to find the ones that match your condition. With an index, it can typically jump almost directly to the relevant rows, which is orders of magnitude faster, especially on large tables.
Makes sense. How can a developer actually figure out if their queries are using the indexes correctly, or if a query is unexpectedly slow?
That's where the indispensable explain query plan command comes in. You prepend this command to any select, update, or delete statement you want to analyze.
Explain query plan select from users where age 30. Like that.
Exactly. When you execute that, SwiftUI doesn't actually run the query. Instead, it returns a description of the query plan it intends to use. It tells you step by step how the database engine plans to fulfill your request.
And what are you looking for in that plan?
You're looking specifically to see if it mentions using an index you expected it to use, like using index Sagen. If instead you see something like scan table users, that's a red flag. It means SQLite decided not to use an index for that part of the query and is resorting to a potentially slow, full table scan.
So it's like debugging the database engine's brain.
Pretty much. It's absolutely essential for professional SQLite performance tuning. Beyond indexing, other basic rules apply. Avoid select whenever possible. Only select the specific columns you actually need. This reduces data transfer and processing overhead.
Good practice, yeah.
And definitely use prepared statements, especially for SQL queries that you execute repeatedly, maybe inside a loop.
Prepared statements. How do they help?
When you send a raw SQL string to SQLite, it first has to parse that string, validate it, and generate an internal execution plan. A prepared statement allows you to do that parsing and planning step just once. Then you can execute that pre-compiled statement multiple times with different parameter values, like different user IDs, much more efficiently, bypassing the repetitive parsing overhead. It makes a huge difference for bulk operations.
Okay, that leads nicely into transactions and data integrity. SQLite is famous for its reliability, often summarized by the acronym ACID.
We need to unpack what ACID compliance actually means because it's fundamental to why databases are trustworthy.
Right. ACID is the bedrock of transactional integrity in most databases, including SQLite. It stands for atomicity, consistency, isolation, and durability.
Okay, let's break those down. Atomicity. Atomicity means that a transaction, which is a sequence of one or more database operations, like an insert and an update, is treated as a single, indivisible unit of work. It's all or nothing. Either all the operations within the transaction complete successfully, or if any part of it fails, maybe due to an error or a system crash, then the entire transaction is rolled back and the database is left in the state it was in before the transaction started.
Okay, all or nothing. Like transferring money, either it leaves A and arrives at B, or nothing happens.
Perfect analogy. Next is consistency. This ensures that any transaction will bring the database from one valid state to another valid state. It won't violate the database's own integrity rules, like unique constraints, or perhaps a rule that an account balance can't be negative. The data remains consistent according to the rules defined.
Makes sense.
Yeah.
Isolation. This sounds like it relates to multiple users or threads accessing the database at once.
It does. Isolation ensures that concurrent transactions running at the same time, don't interfere with each other in unexpected ways. Even though multiple transactions might be executing simultaneously, the system guarantees that from each transaction's perspective, it looks like it's the only thing running. It doesn't see the partial uncommitted changes of other transactions. This prevents dirty reads and other concurrency problems.
Okay, separation. And finally, durability.
Durability is the guarantee that once a transaction has been successfully committed, its changes are permanent. They will survive any subsequent system failures, like a power loss or an application crash. The data is safely stored on non-volatile storage, the disk file.
So atomicity, consistency, isolation, durability. That's why wrapping, say, 1,000 individual insert statements inside a single begin transaction. Commit block is so important.
Absolutely. It's not just vastly faster, because the disk write is often deferred until the commit, but it also guarantees that either all 1,000 rows get inserted correctly, or if something goes wrong halfway through, none of them do. It maintains the integrity of your data thanks to ACID properties.
Got it. Now, there's a more modern SQLite feature that directly addresses some of the concurrency limitations, especially the issue of writers blocking readers. That's wall mode, right? Write-ahead logging?
Yes, wall mode is a significant enhancement for concurrency in SwiftUI. Let's think about the traditional way SwiftUI worked, called rollback journal mode. When a process wanted to write changes, it essentially had to lock the entire database file exclusively.
So nobody else could even read from the database while that write was happening.
Pretty much. Readers would be blocked until the writer finished and released the lock. This could lead to noticeable pauses or stutters in an app, especially if writes were frequent or slow.
That sounds like a bad experience for a responsive UI.
It definitely could be. Wall mode changes this fundamentally. Think of your main SwiftUI database file DB as the primary record book. With wall, when a process wants to write changes, it doesn't modify the main.db file directly. Instead, it appends the new data pages to a separate, temporary file called the writeaheadlog.db-wall.
Okay, so writes go to this separate log file first. How did that help readers?
Because the reader processes can continue to read the last known consistent state of the database directly from the main.dd file, completely concurrently with the writer appending to the wall file.
So writers don't block readers anymore.
Exactly. It dramatically improves read-write concurrency. Readers read from the main file, writers append to the wall file. Periodically, a process called checkpointing merges the changes from the wall file back into the main database file, but this happens efficiently and often in the background.
That sounds like a huge win for responsiveness. Any other benefits to wall?
Yes, writes themselves can often be faster, especially small writes, because appending sequentially to the wall file is typically quicker disk I/O than finding and overwriting pages scattered within the main database file. So enabling wall mode, which most modern wrappers do by default or make easy to enable, is generally a big performance and concurrency win for Slate databases in applications.
Okay, we've covered the Apple stalwart core data and the venerable portable Swaylight.
Yeah.
But in recent years, another player has gained significant traction, especially in the mobile space. Realm.
That's right. Realm burst onto the scene, really marketing itself as a modern, mobile-first alternative database. It promised and often delivered superior performance and particularly ease of use compared to wrestling with core data's complexities or writing lots of SQL boilerplate for SwiftUI.
So what is Realm, fundamentally?
Realm is an open source, mostly, object-oriented database engine designed specifically from the ground up for mobile, embedded, and wearable applications. Its absolute key differentiator is how you interact with data through direct live objects.
Live objects. What does that mean compared to core data or SQLite?
It means there's essentially no explicit object-to-row mapping layer you need to worry about, like you do with ORM's core data or manual mapping SQLite. You define a standard Swift class that subclasses Realm's object base class.
Okay.
And Realm handles the persistence of instances of that class directly. It stores your objects in its own highly optimized custom C++ storage engine. This significantly simplifies the data access layer compared to the other options.
And you mentioned mobile first. A huge selling point for Realm is its cross-platform nature, isn't it?
Absolutely. This is a major reason many teams adopt it. The same core Realm database engine and largely the same developer API can be used across iOS, Swift, Objective-C, Android, Kotlin, Java, React Native, Flutter, .NET, and more.
Wow, that's broad coverage. So large organizations could potentially standardize their local mobile database persistence layer across completely different native development teams.
Exactly. That offers potentially huge efficiency gains in terms of shared knowledge, reusable schemas to some extent, and consistent data handling logic across platforms.
Okay, so how does defining your data model actually look in Realm? You said use subclass object.
It's designed to look very clean and idiomatic in Swift. You define your model class by subclassing object. Your properties, like name, age, email, are declared using @persisted, a property wrapper Realm provides.
@persisted var name, string, like that.
Precisely. Realm uses this wrapper to manage the link between your Swift property and the underlying storage. Relationships are also baked right in and feel very natural.
How do relationships work? One-to-one, one-to-many?
A simple-to-one relationship, like a dog having an owner of type person, is just declared as an optional persisted property @persisted var owner person. For to-many relationships, like a person having many dogs, you use Realm's generic list container type @persisted var dogs list dog.
And that list dog behaves like a Swift array.
It behaves very similarly to a standard Swift array. You can append, remove, iterate, etc. But it's dynamically backed by the database query. It's not loading all dogs into memory at once, which is efficient. #tag_tab Realm's unique features.
Okay, the model definition looks clean. But you mentioned live objects earlier. This sounds like the real aha moment for developers coming to Realm. You said it fundamentally changes how you architect your app.
It absolutely does. It shifts the entire data handling paradigm in your app from being primarily pull-based, where you explicitly fetch data when you think you need it, to being reactive or
Oh,
push-based.
so what makes Realm objects live?
Realm objects, and especially the collections of objects returned by Realm queries, which are of type results your object, are not static snapshots of the data at the time you fetch them. Instead, they are live, auto-updating references that directly reflect the current state of the underlying database.
Whoa, okay, hang on. Let's walk through an example. Say I have a UI that displays a list of active tasks. I perform a Realm query, realm.objects. Task got self-filtered, complete, full, complete. I get back a results task collection.
Right.
Now, somewhere else in my app, maybe a background thread processes one of those tasks and updates its isComplete property to true inside a Realm write transaction. What happens to my original results task collection that my UI is displaying?
Here's the magic. That results task collection on your main thread will automatically update itself. The task that was just marked complete will simply disappear from that collection without you needing to manually refetch the data, rerun the query, or call reload data on your table view.
Seriously, it just updates.
Yes, updates. The query results continuously monitor the database for relevant changes. This is the core concept of Realm's zero-copy architecture. Your objects and collections often directly map to the underlying database data without extensive copying or caching layers in between.
Okay, that's a massive departure from Core Data's FRC needing delegate methods or SwiftUI needing manual refetches. How do you actually react to these changes in the UI then if you don't call reload data?
This requires a structural shift in your thinking. You move away from imperative data reloading and embrace reactive programming patterns. Realm provides a notification mechanism using notification tokens. You attach or subscribe a notification token to your results collection.
Let token results.observe changes in mail.
Exactly. Realm then calls that closure whenever the collection changes due to underlying database rights. Inside the closure, the changes parameter tells you exactly what happened, which indices were inserted, deleted, or modified.
Ah, so it gives you fine-grained change information, similar to the FRC.
Very similar. It provides the precise index-based changes needed to perform animated updates on UItable view or UI collection view using their batch update methods, just like the FRC does. But the key difference is the data source itself, the results collection, is always live and up to date automatically.
That sounds incredibly powerful and could simplify state management a lot. What about querying itself? Is it easier than Core Data's NSFetch request or writing SQL?
Generally, yes, it's considered significantly simpler and more type-safe, especially compared to raw SQL. Realm uses a query language based on string predicates, very similar to Apple's NSPredicate syntax, which most iOS developers are already somewhat familiar with.
So filters like name begins with A and age 30.
Exactly like that. You apply these filters directly to your results collections or when fetching objects using chainable methods like .filter and sorted. It provides a really concise, fluent, and type-safe API for querying your object data without ever having to construct complex NSFetch request objects or manually write SQL strings.
Okay, seems like a lot of advantages.
Sure.
But there's always a catch, right? What's the tricky part about Realm? You mentioned threading earlier.
Ah, yes, the threading model. This is probably the single biggest hurdle and source of confusion for developers new to Realm. Just like Core Data's managed object contexts, Realm instances and the objects fetched from them are strictly thread-confined. They are not thread-safe.
Okay, thread confined. This sounds critically important, maybe even more strict than Core Data's MOC confinement.
It is, in a way. It means that a specific Realm instance, there's Realman, and any object or results collection fetched from that instance are bound irrevocably to the specific thread on which that Realm instance was opened or the object was fetched.
So I fetch a user object on the main thread. I absolutely cannot pass that user object reference over to a background thread and try to access its properties there.
Correct. If you try to access a Realm object or collection or even the Realm instance itself from a different thread than the one it's bound to, your application will throw an exception and crash immediately. Realm is very strict about enforcing this.
Wow. Immediate crash. So how on earth do you perform background work with Realm data? How do you pass information between threads?
You have to adopt a specific pattern. Every thread that needs to interact with a Realm database must open its own independent Realm instance on that thread. Let background Realm try. Realm on the background thread. Let main Realm try. Realm on the main thread.
Okay, separate Realm instances per thread. but I still can't pass the objects between them. So if my background thread modifies a task object, how does my main thread find out or get the updated data?
You cannot pass the managed object itself. Instead, you need to pass a thread-safe indirect reference to the object. The most common way is to pass the object's primary key value, which is usually just a simple string or int.
Oh, so the background thread gets a primary key of the task it updated, passes that key, the string, back to the main thread.
And then the main thread uses its own realm instance and that primary key to refetch a thread local instance of the task object using main realm.objecttype.task.self for primary key.theKey.
Okay, so you pass identifiers, not objects, and refetch on the target thread. That makes sense, but sounds like something you constantly have to keep in mind.
You absolutely do. It's a fundamental part of working with Realm correctly. And one more critical piece. All operations that modify the database, inserts, updates, deletes, must be performed inside a dedicated write transaction block.
Realm.write.
Exactly. Try realm.write, realm.add, new object, existing object.property, new value, realm.delete, old object. This transaction block ensures atomicity. All changes succeed or none do, and makes the changes visible to other threads' realm instances, which will then trigger notifications if they're observing relevant data.
Okay. Thread confinement, pass identifiers, use write transactions.
Ah.
Got it. Steep curve, but the live objects sound tempting. Hashtag tag data synchronization with Realm Sync.
Now, beyond the local database features, the absolute killer feature that truly sets Realm apart from standalone core data or SwiftUI is its optional integrated cloud synchronization service, Realm Sync.
Realm Sync. Okay, this sounds like it tackles a whole different problem domain, getting data off the device and into the cloud and keeping things consistent.
Precisely. Realm Sync is designed to enable automatic, near real-time, and importantly, bidirectional data synchronization between the local Realm database living on the user's device and a managed MongoDB Atlas database running in the cloud.
MongoDB Atlas. So Realm is tightly integrated with MongoDB's cloud platform now.
Yes. Since MongoDB acquired Realm a few years ago, the integration has become very deep. Realm Sync essentially turns your local mobile Realm database into a continuously synchronized client for a MongoDB Atlas backend cluster.
What's the primary goal or use case for Realm Sync?
It's primarily designed for building robust, offline-first mobile applications. That means your app remains fully functional, able to read and write data, even when the device has no internet connection.
Okay, offline first is huge. So if I'm on a plane with no Wi-Fi, I can still add new tasks, mark tasks complete, edit notes, whatever my app does.
Yes, you continue interacting with your local Realm database just as you normally would. Then, the moment your device regains connectivity,
Realm Sync automatically kicks in the background and syncs all those local changes up to the MongoDB Atlas cloud.
exactly. And just as importantly, it also pulls down any changes that might have happened in the cloud while you were offline, maybe changes made by another user on another device, or through a web interface connected to the same backend.
Wow. And it handles this synchronization automatically. What about conflicts? What if I edited a task offline and someone else edited the same task via web app while I was offline?
That's the really hard part of synchronization, and Realm Sync has built-in conflict resolution strategies to handle it. The default strategy is typically last write wins based on timestamps, but more sophisticated custom resolution logic can sometimes be implemented on the back end if needed. The key is that it guarantees that all clients will eventually converge to the same consistent state without the mobile developer having to write tons of complex conflict handling code.
That's a massive burden lifted.
Yeah.
How does Sync manage security and decide which user gets to see which data? You don't want one user syncing down another user's private notes.
Right. It relies heavily on user authentication. Realm offers various authentication providers, email password, Apple, Google, custom JWT, etc. Once a user is authenticated, Sync typically uses a concept called partition-based sync.
Partitioning.
Yeah.
Like dividing the data up.
Exactly. You usually structure your data in Alice and configure Sync such that each piece of data belongs to a specific partition, often based on a user or field, or maybe a projected or teamid. When a user logs in on their device, their local Realm Sync session is configured to only synchronize data for the specific partitions they have access to, e.g. a partition key equals logged in usered.
So it automatically ensures that the device only downloads and uploads the subset of data relevant and permitted for that specific authenticated user.
Precisely. It keeps the local dataset secure, relevant, and manageable in size, while allowing potentially huge amounts of data across all users to live in the Atlas backend. This combination of offline first capability, automatic real-time sync, conflict resolution, and secure partitioning makes Realm Sync an incredibly powerful end-to-end solution for building collaborative, cloud-backed mobile applications with significantly less effort than trying to build a similar sync engine manually on top of Core Data or Spotlight.
Okay, we've spent a lot of time talking about the different database and persistence frameworks themselves. UserDefaults, Keychain, Core Data, Squalite, Realm. But where this data actually lives on a device and how efficiently it gets written and read is just as critical for building a well-behaved app. We need to understand the iOS sandbox environment.
Absolutely. The sandbox is fundamental to iOS security and privacy. Think of it as a secure container, a walled garden that completely isolates your application and its data from other applications and from the core operating system itself.
So my app can't just go snooping around in another app's files.
Yeah. No, it prevents that entirely. Your app lives within its designated sandbox, and within that sandbox, iOS provides a set of strictly defined directories, each with a very specific purpose, especially regarding data persistence, backups, and when the system might clean things up.
Okay, let's break down these key directories inside the sandbox.
Yeah.
Which ones can we write to and which are read-only?
Right. First, the main read-only area. The app bundle itself, which usually ends in .app. This contains your compiled executable code and all the stata resources you shipped with your app images, sound files, storyboards, maybe preloaded data files.
And crucially, it's read-only at runtime.
Absolutely read-only. Once your app is installed, you cannot modify, add, or delete anything inside the app bundle. It's sealed.
Okay, so that's for shipping static assets. What about the writable areas where we actually store data?
There are three main writable locations we need to care about. First, and perhaps most important for user data, is the Documents directory.
Documents. Sounds like it's for user documents.
Pretty much. Apple intends this directory specifically for user-generated content that the user explicitly creates and would expect to keep. Think text files they wrote, drawings they made, photos they edited within your app, maybe important PDFs they saved.
And what's special about the Documents directory regarding backups?
This is key. By default, the entire contents of the Documents directory are automatically backed up to the user's iCloud account, if they have iCloud backup enabled, and also included in local iTunes Finder backups.
Ah, so stuff here is relatively safe and preserved.
Yes, it's meant for essential user-created data that shouldn't be lost. However, this also means you should be careful not to dump huge amounts of non-essential or recreatable data in documents, because you'll bloat the user's backups unnecessarily.
Right, so if I'm downloading, say, large amounts of cache data like map tiles or article content for offline reading, that shouldn't go in Documents.
Definitely not. You'd be wasting the user's iCloud storage and significantly slowing down their device backups. That kind of transient downloadable or easily recreatable data belongs in the library directory, specifically inside the library caches subdirectory.
Library caches. Okay, what's the rule for caches?
The caches directory is for exactly that. Cached data. Temporary files, downloaded assets your app needs for performance, but could potentially re-download if necessary. The crucial difference from Documents is that the contents of the caches directory are not backed up to iCloud or iTunes.
Not backed up. Got it.
And even more importantly, the operating system reserves the right to delete the contents of your app's caches directory if the device starts running low on storage space.
Whoa, okay, so iOS can just wipe my cache if it needs space.
It can, and it will, without warning. Therefore, you absolutely cannot rely on the caches directory for storing anything essential or user-critical. It's purely for performance optimization data that your app can survive without or regenerate.
Okay, Documents for user data, backed up. Caches for recreatable data, not backed up, purgeable. Is there anywhere else? What about truly short-lived temporary files?
Yes, there's also the chimp directory, temporary directory. This location is intended for files that are only needed during a single session or a specific short-term operation. Think maybe partially downloaded files before they're fully assembled, or intermediate files used during a complex processing task.
And how temporary is temporary?
Very temporary. The system is quite aggressive about clearing out the chimp directory. It might wipe its contents whenever your app is suspended, terminated, or sometimes even just during regular system cleanup routines. You should assume files in chimp can disappear at almost any time the app isn't actively running.
Okay, so understanding the distinct purpose and behavior, especially regarding backups and purging of documents versus caches versus temp, is absolutely vital for being a good iOS citizen and ensuring data is stored appropriately.
Vital. Storing cache data in documents is one of the most common mistakes leading to backup bloat and slow syncs. Hashtag tag tag BIO performance optimization.
Now, regardless of which persistence framework you use, Core Data, SQLite, Realm, or which directory you're writing to, the act of input-output reading from and writing to the flash storage can often become a performance bottleneck, if not handled carefully.
Absolutely. Disk I/O is inherently much slower than accessing RAM, so optimizing it is crucial for a responsive app.
What's the absolute #1 principle for I/O performance on iOS?
The same golden rule we see everywhere in iOS development: avoid blocking the main thread.
Never do slow work on the UI thread.
Never, ever. Any potentially slow file operation, reading a large file, writing significant amounts of data, even sometimes just checking if a file exists if the disk is busy, must never run synchronously on the main application thread. If you do, you will block the UI, leading to freezes, stutters, and a terrible user experience.
So how do we perform I/O then?
All non-trivial file reads and writes must be dispatched asynchronously to a background queue. You can use Grand Central Dispatch, GCD, Operation Queue, or the modern Swift concurrency features, async-await with background actors or tasks, to achieve this. Get that I/O off the main thread.
Okay, backgrounding is essential. What other techniques can optimize I/O performance itself?
Several things. If you need to process very large files, don't try to load the entire file into memory at once. Use memory buffers or file streaming APIs. Read and process the file in manageable chunks, a few megabytes at a time, to avoid huge memory spikes.
Makes sense for large files. What about lots of small writes, like updating many small configuration files or logging frequent small events?
For that, you want to batch small writes. Hitting the disk repeatedly for tiny amounts of data is inefficient. It's often much better to accumulate those small changes in memory, in a buffer or queue, and then write them out to disk in larger consolidated chunks periodically or when the app is backgrounded.
Reduce the number of actual disk write operations.
Exactly. We also already discussed the benefits of enabling wall mode for SQUID databases. That's a direct I/O optimization that significantly improves concurrent read-write performance.
Right, wall mode helps SQUID.
And finally, leverage caching effectively. For data that's expensive to compute or load from disks but is accessed frequently, use caching mechanisms like NSCache, which is memory aware, or even just storing pre-processed results in the caches directory, keeping in mind it can be purged, to avoid redundant disk hits or computations. Hashtag see modern networking with URL session.
Okay, one last piece of the puzzle. Before data can even be persisted locally, it often has to arrive over the network first. For modern iOS networking, the framework of choice is URL session.
Yes, URL session is Apple's current definitive high-level networking API. It effectively replaced the older, now deprecated NSURL connection framework several years ago.
Why the change? What makes URL session better or more modern?
URL session was designed from the ground up to be more flexible, more efficient, and much better suited for modern asynchronous programming patterns, including background operations. Its architecture is built around the concept of sessions and tasks.
Sessions and tasks. Break that down.
A URL session object represents a configuration for making requests, like setting timeouts, caching policies, handling cookies. From a session, you create specific task objects for individual network operations. There are different types of tasks for different needs.
What kinds of tasks?
The most common is a URL session data task. This is for fetching relatively small amounts of data, like JSON or XML responses from an API, directly into memory as a data object. Then there is a URL session download task.
Download task. So it sounds like it's for bigger files.
Exactly. Download tasks are optimized for fetching large files. Instead of loading the entire file into RAM, they stream the downloaded data directly to a temporary file location on disk. This is much more memory efficient for large downloads. There are also URL session upload tasks for uploading data or files.
Okay, different tasks for different jobs. But you mentioned a major benefit over the old NSURL connection was background handling.
Precisely. This is a killer feature of URL session. It has built-in first-class support for background transfers using special background session configurations, URL session configuration.background with identifier.
What does that enable?
It means you can initiate a potentially long-running network operation, like uploading a large video file or downloading a big data update, using a background session task. If the user then switches away from your app or even locks their device, the operating system's networking daemon can actually continue that transfer in the background on behalf of your app.
Wow, so the transfer doesn't necessarily stop just because my app got suspended.
Correct. The OS manages it. When the transfer completes, or if it fails, the OS will relaunch or wake up your app in the background and notify your app delegate, allowing you to handle the completed download or upload. This is crucial for reliable large transfers, minimizing data usage issues if the user switches networks, and just providing a much better user experience.
And where do those background downloads end up?
The URL session download task, both foreground and background, automatically saves the completed file into a temporary location, often within the app's TMP directory, respecting the sandbox rules. It then gives your app the file URL to that temporary location, and it's your app's responsibility to then move that file to a permanent location, like documents or caches, before your completion handler returns, because the temporary file will be deleted otherwise.
Okay, so URL session provides the modern, efficient, and background-capable foundation for getting data into the app, ready for persistence using one of the frameworks we discussed.
Exactly. It completes the picture from network to storage. Hashtag tag outro.
All right, that was a serious amount of synthesis we just performed. A true deep dive. We journeyed all the way from the simplest key-value preferences stored in user defaults.
Making sure to highlight the critical security boundary leading to the hardware-backed keychain for anything sensitive.
Then we plunged into the structured data world, exploring the object-oriented complexity, a rich feature set of core data, especially its relationship management and UI integration with FRCs.
Contrasting that sharply with the low-level relational control, raw SQL power, and cross-platform portability offered by SwiftUI, remembering the importance of indexing and wall mode.
Then we examined the modern, reactive, live object approach of Realm, highlighting its ease of use and particularly its powerful Realm sync capabilities for offline-first, cloud-backed apps.
And finally, we grounded everything by looking at the app's environment, the crucial role of the iOS sandbox directories, documents, caches, tep-cap, for proper file management, backups, and system citizenship, plus a nod to URL session for getting data there in the first place.
Whew, that covers the landscape pretty thoroughly.
I think the overarching synthesis, the key takeaway here is really clear. There is absolutely no single best tool for all iOS data persistence. The choice must be a deliberate, informed decision driven entirely by the specific needs of the data you're handling.
You need to ask the right questions first.
Exactly. How sensitive is the data? How large is it? How structured is it? Does it have complex relationships? Does it need to be transactional? Do you need under-ADO? Do you need offline cloud sync? Does it need to work on Android too?
Right. Core data shines when you're deep in the Apple ecosystem, need robust object modeling, and want tight integration with UI frameworks. SwiftUI offers that raw speed, control, and portability, but makes you build more infrastructure yourself. Realm strikes a fascinating middle ground, offering object simplicity, live updates, and that unmatched built-in sync, but with its own strict threading rules.
The nature of the data dictates the tool.
So what does this all mean for you, the listener? You now possess, hopefully, a comprehensive mental framework to conduct that essential cost-benefit analysis before you write a single line of data persistence code.
You understand why misusing user defaults can cripple your app's launch time. You know why respecting thread boundaries in core data and Realm is absolutely negotiable to prevent crashes and corruption. You see how enabling wall mode and SwiftUI can make your UI significantly smoother under load.
You're equipped to make better architectural choices.
And here's maybe a final provocative thought for you to mull over until our next deep dive. We touched upon migrations handling changes to your data schema over time. We noted that core data offers some lightweight automatic migration capabilities, and Realm generally manages schema versioning and migration with relative ease through its API.
But with Direct Slate.
With Direct Slate, every schema change, adding a column, renaming a table, changing a data type requires you, the developer, to manually write, test, and execute potentially complex alter table SQL commands. You also have to meticulously track schema version numbers yourself and build the logic to apply those changes incrementally when a user updates the app.
That sounds like significant ongoing maintenance effort, especially for an app that evolves over many years.
It absolutely can be. So the question to ponder is, given the inevitable evolution of almost any successful application, how much weight should a developer give to this potential long-term maintenance cost of manual migrations when making that initial foundational data storage decision between, say, Scala and core data or Realm? Is the initial simplicity or control of Scala worth the potential decades of migration headaches down the line?
Something to definitely think about. How much do you value future ease of evolution versus initial implementation choice?
Exactly. A fascinating trade-off to consider.